optical barrier.
We'll worry about that later.
All right, fine. Thanks. Thank you. I appreciate the opportunity to talk to you all today. I'm going to be getting away from the science a little bit and talking about the impacts and the societal consequences of space weather. So it's going to be a little change of pace here. This issue of space weather has taken on a new meaning across the United States and indeed the world over the last few years. And it's largely because of our reliance on advanced technologies for everything we do today. What we've done is we've created a vulnerability in this country, perhaps more so than any other country, because we do rely on the GPS, on those satellites, on the electric power grid. If we didn't have any one of those technologies for any length of time, the consequence would be very, very significant. We recognize space weather can have an effect on those technologies. Somebody said to me last week, they said, you know, if we lost electric power for an extended period of time, it would be just like being back in 1850 when we had no electricity. I said, no. It wouldn't be like that at all. Because back in 1850, people knew how to live without electricity. We go without electricity for any length of time, the consequence, of course, will be very dire. I think I learned about how much space weather has progressed across this nation, and some of you might remember the March 2012 activity. We haven't had a whole lot of space weather this particular solar cycle of note, but we've had a couple of moderate outbreaks. One of them was December 2012, and things change in the Space Weather Prediction Center when we get some activity. I think we're very much like a fire station, with people hanging around not doing a whole lot of work, and then all of a sudden the fire alarms go off, of course the solar flare activity, and things start really hopping. And that was the case in March of 2012. And we are the center for civilian and commercial world Space Weather Service Center here in Boulder. So all the questions come into us, all the media interest come into us, and all the customers and whatnot. So we staff up our forecast center. I'll go in there, a couple of other senior folks will join the forecasters in the operations center and help them essentially 24 hours during these outbreaks of activity. And we got a call, and someone said, Bill, would you take it? And I did take it. It happened to be our leadership, NOAA leadership in Washington. And I really wasn't interested in speaking with them at that point in time because I was dealing with customers, I was dealing with the airlines and the power grid. And I got on the phone a little bit irritated, and they had a few questions for me, and I asked, well, who wants to know? He said, the president. I said, the president of what? The president of the United States. I said, oh, okay. So yeah, it turned out that in the president's morning briefing, space weather was included on there. And he had some questions. He knew a little bit about it because he had been briefed on it, but his chief of staff, McDonough, had to get back with NOAA leadership, who got back with us to answer the president's questions. So I said, wow. So that's the level of interest where we're at here. And again, it's largely because of our reliance on advanced technologies and the vulnerabilities with those technologies. Lika has her hand. I'm not taking any questions, Lika. Okay.
So you like hurricanes, we like to name our solar storms. With the March, it's called St. Patrick's Day.
Yes, yeah, no, it's probably, it was the first week of March. But it's right, just like the name hurricanes, like in the big space weather outbreak in October 2003 was the Halloween storms. And the 14, and where's the history buffs here? 14th of July is the anniversary of what? All right, so we had the big event in 2000. We call it the Bastille Day flare. But yeah, the St. Patrick's Day activity in 2012. Anyway, so what I'm going to cover here over the next 45 minutes or so, I'm going to talk a little bit more, expand a little bit on this issue of the growing interest in space weather, a little bit about solar cycle 24, and each step of the way here, remember, it's all about the operations side of the house, how it applies to various sectors around the nation. And the space weather types and impacts, I'm just going to go through the three different types of space weather. You've already covered a lot of this. I'm not getting into the science or anything behind it, what I want to do is show you an example of flare, and then what? I want to show you what happens, so what technologies. And then we'll finish up with a little bit on the government response. A lot of things are happening across the highest levels of government in the United States and indeed around the world in response to this threat. So let's talk about sticking with this theme of growing interest in space weather. On this plot here, you'll see going back to 2000, the dark black line being the solar cycle. Our last solar maximum was back in 2000, 2001. Then we went through a prolonged minimum, and of course we're back into the solar maximum right now. But when I show you that shaded area, focus on that. That's the product subscription service. In the Space Weather Prediction Center here in Boulder, we have that, a product subscription service, where people sign up for the alerts and warnings. And you can see the kind of growth from when we introduced this back in 2005. Last month, I just got the report a few days ago, and we were at 550 new subscribers for this past month. And that's the rate of growth that we're seeing and interest. So we've got over 40,000 subscribers now. And you might say, well, who are these subscribers, Bill? And just to kind of give you a snapshot, just to give you some idea of the diverse nature of this customer base, and you will see, well, a lot of things here. You'll see anyone involved in aviation, whether you're regulating the industry, you're building the planes, or you're flying the planes, you need space weather information. Satellite companies, every satellite company, bar none, get the alerts and warnings. They have to understand what kind of environment their satellites are operating in. When you see shipping companies, banking, automobile industry, precision agriculture, what's that about? GPS. GPS has changed society. GPS pervades society. And we are seeing, it's one of the most fascinating aspects of my job, is almost weekly I get a call from somebody, and it's always weird, about how we're trying to understand how space weather is going to affect their technology. It always comes down to GPS. One of the most interesting stories I had was last year. We were actually in Alaska with the Alaska State Department of Transportation. Anyone from Alaska here? Anyone know where Thompson Pass is in Alaska? It goes down into Valdez, a treacherous stretch of road. 1,000-foot drops either side. You get 500 inches of snow there every year. They got to keep that road open. It's the only way in and out of there during the winter for emergencies. So during the many, many hours of zero visibility, close the road to the public. Out come the Department of Alaska snowplows up Thompson Pass. 20, 30 miles an hour, plowing that snow. 1,000-foot drops either side, and the driver's not looking out the window. He's relying exclusively on GPS projected onto his windscreen. It's a terrific system. It's got a 10 centimeter accuracy. So if they veer too far left or right by more than 10 centimeters, it's got a triple alarm. It's got an audio, buzz, got a visual, green light, red light flashes. The third piece I thought was kind of cute when they explained it to me. It has a vibrating seat that gives you a jiggle on one side if you're too far left. And so it makes sense. But to these guys, so GPS is a matter of life and death. GPS is off. I did have to ask the question, if you're thinking about it now, you say, well, what if there's a moose on the road? This is what we got radar to, Bill. This is it. So they actually have radar systems. But, it's just an example of how GPS. I got another call from a guy who's managing a golf course in California. He wanted to sign up for the alerts and warnings. I said, why? He says, we're putting GPS in our golf carts. Seems like cheating, doesn't it? But when you get down the fairway, for those who can play golf, are on the fairway. I'm never on the fairway. But you got your marker telling you how far away you are from the hole. Of course, if you have your little GPS in your golf cart, it'll do the same thing for you. So he wanted to have a sign up that said the weather conditions at the first hole, as well as the space weather conditions for GPS reliance. But again, I could spend the rest of the day talking about how GPS gets impacted, and the various customers that sign up for the alerts and warnings that rely on GPS. It is really quite fascinating. I want to give you a couple examples. I didn't touch on the precision agriculture because I wanted to show you as an example. I always like to use a little bit of testimony. Not Bill Murtagh's words, but the words from the customers themselves. And this was an email that came in April 2. I think that was following the St. Patrick's Day 2012 storm, right? But you can see that these guys work in here's how it works with the tractors and the GPS. They're using high-precision GPS to plant seeds now. So that tractor's going along, it puts drops of seed using that GPS, and then they'll come behind it, irrigating and fertilizing exactly where the seed is, using that kind of efficiency with GPS, centimeter accuracy. Consider how efficient that is versus spraying and whatnot. And think about this too, it's a very important element that these folks explained to me. They can do it 24 hours a day. There's no more worrying about being up at sun up and sun down because you're relying on GPS. Doesn't matter if it's dark out. So these folks are plowing fields now 24 hours. Anyway, when we get geomagnetic storms, when we get disturbances in the ionosphere, it can have a fairly profound impact on GPS. And they realize that. So these folks here wanted to set up a process where they would get our alert. Something I would like to explain to people. When we talk about 40,000 subscribers, one of them could be this North Dakota equipment dealer who in turn sends it out to hundreds or even thousands of his customers so that they understand today is not a good day to use GPS. Drilling and survey operations is another biggie. If I look at that product subscription service, I will see Shell and Exxon, British Petroleum, Schlumberger, all the biggies. They all use GPS for drilling operations. What kind of money they said? Look, they said, Bill, if things are wrong on the GPS, it could knock us back $1 million for one operation. Because they're assuming the conditions are good and they're not. Interesting, not only GPS, but they also have magnetometers on the drilling heads, rely on accurate magnetic field measurements. So not only does the effect on the ionosphere and the GPS cause them grief, even just the magnetic field disturbances on their magnetometers and their drilling heads. And the 2012 activity, just one last piece on that. Satellite industry, a lot of times people don't realize these things are happening. They don't go public with them too often. But we had a fairly profound effect on a satellite back then. It was on the SkyTerra 1, which is the light squared satellite. By some accounts, the biggest communication satellite in orbit right now. And it got impacted during the space weather activity, and they thought it would only be out for 24 hours. It turned out to be down for about 3 weeks or so. So again, if you're depending on that system and it's down, it can have a fairly significant effect. All right, so I just wanted to cover some of this. I'll talk a little bit more at the end of our discussion here about the growing interest and the government response. But let's jump into the solar cycle, again, from the operational perspective. What does it mean to the average person out there? You can see that this solar cycle, as you know by now, is fairly small. By some accounts, it may be the smallest in the last 100 years or so. But, so what? This is a very important message when I'm on the Hill or in Washington, have to explain this to decision makers up there, is that we can have fairly big events with small solar cycles. And I like to show them this plot, and that shows 250 years of solar cycles, and the red dashed horizontal line is the average. And if you look at two particular cycles, in 1859, 1921, and you recognize 1859 is the year of the Carrington event. And another tremendous storm occurred in 1921, and just recognize that those particular storms occurred with smaller than average cycles. So the point, the takeaway, of course, is don't let your guard down, because people will. You'll see things, the press mess this stuff up big time. And they'll suggest that we're a smaller solar cycle, well, nothing to worry about. We see less activity, no question about that, but we could still see a very big event. 1859 storm, I don't know if you guys have covered much on that yet, but we actually had measurements in the Kew Observatory in London from that particular storm. It has changed the way we do business in the Space Weather Center. Now let me explain to you why, just before it's probably as good a point as any to explain this to you. In the Space Weather Center in Boulder, I've kind of put our responsibilities in two bins. One is the day-to-day activities. We have two people working the desk 24 hours, 7 days a week, issuing alerts, warnings, forecast. Remember, all clears are very important too. Every day during solar minimum, people are still looking to see what the forecast is, so we're saying nothing's happened. So that part, day-to-day activities. The other bin is the one that's driving all sorts of interest in government, at the highest levels of government. That is the potential for an extreme event, for a Carrington-like event. If it should occur today, what would the consequence be? Wasn't much talk about the Carrington event back in the last solar cycle. Bruce Serratoni from NASA, a few others looked at this Carrington event back in 2003, 4, 5 time frame, and they suggested that the event was maybe as big as 4, 5, 6, 10 times as anything we've seen recently in the space age anyway. So the next logical step, of course, was the engineers would take a look and say, well, what if we had an event of that magnitude today? What would it do to the technology we rely on? And the suggestion was, by some accounts, the impact could be catastrophic, especially with the power grid. And that got the attention of the White House and leadership around the world. So recognize that when I highlight that issue of this Carrington event, they can occur at any time, even with smaller cycles. And the other thing, another takeaway that I want to share with you, a misconception about the solar cycle. When do the biggest geomagnetic storms occur? Is it at solar maximum? Is it at solar minimum? When is it? So what I do is I like to show this. This is the occurrence of the K7 geomagnetic storms across solar cycle 21 from 1976 to 1986. Can you pick out solar maximum? You probably wouldn't have picked right there. But the point being, of course, that big geomagnetic storms can occur at any stage of the cycle. There's a bit of a lull during solar minimum, but we can see big events 3 years prior to sunspot maximum, 5 years after. So again, we have to explain to our people, our leadership, don't let your guard down because we're past solar maximum. Yeah, there's certainly much. Yeah, could a big event occur in an extreme, prolonged period of low activity, like the Maunder minimum? Have you guys talked Maunder minimum? Okay, so it was a 90-year period, 1640 to 1750, no sunspots. Certainly, the criteria is sunspots. I mean, for the big activity, when we talk about the Carrington event, the Halloween storms, the Bastille Day, they're all associated with big sunspot clusters. There was very little of that during that 90-year period. So while I would say never, I would certainly not say it couldn't, the likelihood would have been extremely small. If we don't have the big sunspot clusters, we're not going to see it. The 1921 storm is interesting. We look back in the history books, I always find this fascinating because, of course, back in 1921, there was advanced technologies too. Did the advanced technologies of the day back then get impacted by space weather? Yes. Look at the article here from the New York Times in 1921, and we read halfway down there, the entire signal and switching system of the New York Central Railroad below 125th Street put out of operation, followed by a fire in the control tower due to geomagnetically induced current. It's interesting, the New York Central Railroad is, there's a big meeting coming up in London in later this year with railway companies and Department of Transportation around the world to address the issue of railway vulnerabilities to space weather. So it's still an issue. And of course, our friends in Canada and Alaska are very familiar with the Northern Lights, the Aurora Borealis. Imagine what it was like in May of 1921 when the folks in Cuba and Jamaica looked up and saw the Northern Lights. So it's just a reflection of how intense that geomagnetic storm activity was.
During these very intense times, does the polar cap get less active?
What? Yeah, it actually does. And it's interesting, again, from the customer perspective, when we'll see our airlines, when they're flying north, especially the polar operations, will encounter lots of problems at the very high latitudes. But during some of the extreme, including the Halloween storms, they had good comms when they got past the Aurora Oval, which extended so much further south. So it depends, obviously, the interaction between the energetic particle event that might occur and causes the polar cap absorption, as well as the Aurora Oval activity, It gets pretty complex. We hate having to talk to the airlines and explain that one to them, why it might get better. Yeah. So the last takeaway here with the solar cycle is it links back to something I said a few minutes ago, in the big events can occur with smaller cycles. This thing here was a blessing in many ways. The blessing that it didn't hit us, this July 2012 event, I'm not sure what the consequence would have been, but it's also a blessing that I can show people that yes, big events can occur because they just did. And they say, well, we didn't hear anything about this July 23, 2012 event. It must not have been that big. Well, of course, the reason was it didn't hit us. Thanks to the stereo mission, because we were looking at the sun that day, and that image you see there of the sun was the image that particular day. Do I have a... Oh, okay. Well, not that you know, it's hardly worth picking up the pointer to show you that that was the single sunspot, that one, and it was a little sunspot there, but that was it on the sun. So all of a sudden, we're looking at the coronagraph, we're looking at our particle sensors, they're rising. I see this fantastic coronal mass ejection. We knew right away from the LASCO image alone, this was big. Fortunately, we had the stereo spacecraft, and we could look, and we could see on the backside of the sun a tremendous eruption. Dan Baker, right here from CU, and others looked at this, just published a paper on it, and suggested it was at a powered Carrington-like event. That CME was moving about the same speed. The CME from the Carrington event made that Sun-Earth transit in about 17 and a half hours. This particular event, right around 19 hours thereabouts, from Sun to the stereo spacecraft. So yeah, again, the takeaway being big events can occur. They did. Perfect storm has to include it's Earth-directed. And this other big question that FEMA, others will ask in leadership circles, what's the probability? If I'm going to factor this into any kind of a risk assessment, I have to understand, is this a 1 in 1,000 year, 1 in 10,000 year? What are we talking about, Bill? And when I put these numbers up, it's startling because they're high numbers. When we start talking about 6 to 12% chance of a Carrington-like event in the next 10 years, it gets people's attention. All right, let's transition just a little bit now. Fran, what's my time frame here so I keep an eye on it? It was a panic. I was outside not paying attention, and I had to come running in.
We've got some flexibility, so...
Okay.
Just go on.
Just go on. All right. Good. I don't want to see the big hook coming out here. So I said I'd talk a little bit about the different types of space weather from the operational perspective. What we look at is, of course, the electromagnetic radiation across the spectrum, energetic charged particles, the magnetic field, how it impacts the ionosphere and the magnetosphere. Basically, that's it from the operational perspective. We introduced these space weather scales back about 15 years ago that essentially covers those three types of emissions. The radio blackouts is the solar flare radio blackouts, the electromagnetic emission, the radiation storms is the protons, and the geomagnetic storms, of course, from the CMEs and the magnetic field. These scales have proved to be valuable in the circles in Washington, because remember, when we're dealing with the Hill and we're dealing with emergency managers, most of these folks don't have science backgrounds. They might have legal backgrounds, various professions that don't involve much in the way of science. So I've got to give them something that they can use, and these scales have turned out to be pretty good. They, 1 through 5, 5 being extreme. And again, when we're targeting emergency management folks, and even this regular citizen, people in this country know what an F5 tornado is, right? And when you start talking Category 4 hurricane, it means something to somebody. So we introduced this. We tried to do something that made sense right off the bat. 1 through 5. 1 being minor, 5 being extreme. And the center column, I mean, this stuff gets very confusing for these people very quickly. What types of technology gets impacted by the solar flares at the power grid? Anyway, we try to help them with these scales, so we give them some sense of what will be impacted in that center column. And the last column on the right-hand side, again, the risk assessment, you got to know this. What are we talking? Give me some perspective. Is this like once every 50-year type storm? And you'll see there, like a G5 extreme geomagnetic storm, we'll see about 4 of them per 11-year cycle. So they're the 3 scales covering the 3 types of emissions from the sun that from the operational perspective is most important. And now we'll just take a look at a couple of them and see the impact on various technologies. The solar flare radio blackout, it's not hard to look at the SXI image here and see where the flare occurred. It was a rather bizarre day. I do remember it back in 2005 because we were looking at the sun that morning and we saw nothing of interest on the face of the sun except for that bright area coming around and then that. A fantastic X17, I believe, flare occurred on the limb. Doesn't matter where it's occurring. If we're seeing it, we're feeling it across that electromagnetic spectrum. When we get a blast of emission from a flare of that magnitude, we are going to see GPS impacts. We are going to see communications and ground-based communication systems problems and radar as well. The radar perspective is kind of interesting. I don't think there'll be much focus this week on national security concerns, but I can tell you they're there. Obviously, when we're talking GPS and SATCOM and communications period, it is significant. It is of significant interest to national security interest around the world, and certainly here in the United States. Radar systems, we got 2 minutes. When we get a big eruption on the sun, we got 2 minutes to get that information to the DoD so that we know what's causing the problems with our radar is the sun and not anything else, any kind of jamming device and whatnot. So it's a very important piece of what we do. When we see the flare, on the very, very biggest flares, we will get emissions across the spectrum. We'll get the X-rays, we'll get the extreme ultraviolet, we'll get the radio waves, and they all have different consequences right here on Earth. And I wanted to show you a couple. I wanted to show you how it affects the aviation. And if you look at the plot on the upper right-hand side, the map of the Earth, and look at Central America, it might be a little bit hard to see, but a little yellow dot, the subsolar point on this given day when the flare occurred. It's a daylight side effect on Earth, but that yellow dot represents where the sun was shining directly down on when this flare occurred. The color bar on the bottom reflects the high-frequency radio scale, which is essentially 3 to 30 megahertz. A lot of people use that. We just call it HF, high frequency. When that plot lights up in the yellow and red, especially the red, all HF capability is lost. I'm just going to put it into motion. The big flare occurs. Within a minute of it occurring, this is what this plot looked like over the course of the next 3 hours. Just a wipeout of HF comms. One of the bad things from anyone that gets into the research business here, one of the holy grails is this problem right here. 5 minutes before that flare erupted, we didn't know it was going to erupt. We saw the sunspot, we measured its complexity and its size, its evolution over the past 24 hours. We knew there was potential there, but 5 minutes before it erupted, we did not know it was going to erupt. This thing explodes, it lights up the ionosphere, HF capability is knocked out, and I got folks on the phone saying, Bill, why didn't you give me a heads up? This was coming. I said, I can't. So the best we could do is alert these folks and tell them it happened so they know what's causing the problem. Because it's very important to certain sectors, and here's one of them. The communication sector, if you're flying over the Atlantic or the Pacific Ocean, you're in an airplane, HF communication is the primary means of communication between air traffic control on the East Coast and the West Coast, Long Island, San Francisco. We use HF because we can bounce it over the ionosphere. It counts for the curvature of the Earth. I asked the airlines, how come you guys don't use SATCOM? It's 2014. Aren't we there? Satellite communications? He said, yeah, we're there, Bill. Most of the planes have SATCOM, but at cost. HF is free. So it is still the primary means of communication, and it works great most of the time. It does not during a solar flare. And just to give you an idea, the type of impact That's again, I like their testimony. That's how they described it. Solar activity severely impacted all HF comms. 24 aircraft position reports from New York City, air traffic control delayed via SAT voice between 1410 and severe operational impact. Every time we get a flare, in any mid-level range at all, it affects communications with the aircraft. As soon as it happens, Carol, so they lose capability all of a sudden. So their ability to tell an aircraft to go from 39,000 feet to 35,000 feet is compromised. So it's an immediate safety of flight issue. So they have a whole series of things then that they must do. And that's part of the reason why it's hard to see, but on the lower right-hand side, we give them an estimated recovery time. But they leave in certain situations, such as Halloween storms, there was so many flares day after day, they brought in extra staff to manage the consequence. But they have to go, one of the big things they do, for example, that requires additional staff, they've lost this capability, but they still have line of sight communication capability. So they'll tell Delta 490, who'd be up over Long Island, to talk to American 623, who's over Boston, to tell Delta 652 over Newfoundland to drop down to 350. So it'll just be a relay that they'll set up, and it gets very cumbersome and whatnot. So there was big long wires. Yes, it would. Now the GPS effects remember we're still in this solar flare part of the discussion here and its impact on technology. So we talked about the sun, and the last consequence when we talked about the effect on the ionosphere was the X-rays, the extreme ultraviolets, further ionization, ionizing the ionosphere, essentially changing the characteristics and becomes such a problem, but totally different impact here. The sun is also emitting across the radio frequency range. GPS, we got 24 spacecraft up there in orbit, providing tremendous service with the signal coming down. That signal, it's actually L1 and L2, the two signals, 1.2 and 1.6 gigahertz. The sun emits at 1.2 and 1.6 gigahertz. There is always background noise from the sun at those frequencies. We know that. We engineer around it. It is not a problem. Until the sun explodes like it did in December 2006, that background level at 1.6 gigahertz, we measure it in solar flux units, it's typically about 100. On this particular day, and recognize the date, it was almost solar minimum. I use this as an example too to show people big things can happen in solar minimum. The sun erupted and the background level of 100 solar flux units went to 1 million. We didn't think it could happen. Now picture the signal to noise ratio. Now your signal's coming down, buried in the noise. And it had a profound consequence on GPS systems around the world. I'm going to put this in motion, and what you're seeing, all the green dots, this is the International GNSS service, they're receivers around the world. Green is good, they're getting the signal. I'll put it into motion. You can see in the bottom there the graph, it's the 1.6 gigahertz. You see the little dot moving along. Even with some small bursts, we'll see some impact on some of the receivers, but then all of a sudden the big burst occurs. Sunlit side, northern, southern hemisphere, profound impact on our receivers around the world. Now you look at that, you say 10 minutes. If you're going down the road and you're relying on your TomTom to get you where you're going, and all of a sudden GPS is not working, whoop-de-doo. It's not going to have a profound effect on you. If you're landing a plane in extreme weather conditions and you're relying on GPS and all of a sudden it's not there, then it becomes very, very significant. The consequence of this event, this was a wake-up call. We didn't really think it could be this big. Now we do know it could be this big, and it has changed the way we do business in certain sectors, including aviation. The GIPSOC is the GPS Operations Center at Schriever. They talked about the impact. Several aircraft reported losing lock. They were tracking 7 to 9 satellites, which is optimum. That's what you expect to be able to do, and abruptly lost lock, and we're tracking 0 to 1. All right, so the next piece I want to touch on is the solar radiation storms. Again, from the operational perspective, we see the big flare in October 2003. We're measuring these protons on the GOES satellite. We see a significant increase in the 10, greater than 10, greater than 50, greater than 100 MeV protons. And of course, their focus is going to be more on the polar regions. They're protons, they'll respond to the Earth's magnetic field. The focal point will be the polar regions. 30 minutes to several hours, they can last for days, and the societal impacts here, satellite operations. It's these energetic particles. If I look at that product subscription service, every single satellite company in the world get the alerts and warnings. They have to understand what's causing problems with their satellites during these energetic particle events, because they will penetrate spacecraft and cause impacts. Aviation, I'll just talk about that here in a minute. Communications at high latitudes, poor HF comms. They get impacted with all types of space weather at different latitudes. And of course with NASA, every day at 10:30, we're on the phone with the Space Radiation Analysis Group at Johnson Space Center in NASA, Mission Control. This is their biggest concern, this radiation. This is the radiation that's going to cause problems to the astronauts. And several times in the last cycle, astronauts were directed to hardened parts of the space station during these big energetic proton events. Talk about the airlines. If you're flying from the United States to Asia, typically what route do you take these days? Right over the pole. We've got the planes to do it now. 777s, the Airbus, the 340s, they can fly 16, 17 hours straight. A to B, it's the quickest way to go. Not much in the way of thunderstorms in the North Pole. Don't have to worry about that. Jet stream winds are not an issue. They identified two issues. One, cold temperature impact on fuel, and two, space weather. When we hit that S3 level, if you remember the scales, 1 through 5, when we hit the 3 level, they're out of there. They start rerouting flights away from the poles. Or if they're up there, this is the controversial one, and they get information. Sometimes it's hard to get them the information that we've hit the S3 level. They drop altitude. The concerns to aviation include loss of communication, loss or degradation of navigation systems, even impact on avionics, and then that tricky last piece, radiation exposure. It does increase, and it does increase to a degree that it causes some concern. It's not going to leave anyone with radiation sickness. I made a mistake a couple of years ago of trying to be cute and showed a picture of someone on a plane during a radiation storm, and he was fine at the beginning, and then I showed a picture of John Merrick, the Elephant Man, afterwards. People were horrified. They thought that's what could happen during a proton event. Of course not. But here's what happened. One of the big things that has changed the dynamic here was that a report came out from the Royal Academy of Engineering in England just last year, and they suggested the extreme event could produce 20 millisievert dose increase. That's the annual allowance for a radiation worker. Now, if we got half of our pilots up in flight during a radiation storm and we get that kind of dose rate, we got a big problem. So that's become a very significant concern. We're meeting in London on the 9th and 10th of October with the FAA and the FAA equivalent in the UK, the Civil Aviation Authority, with the White House, and with the Cabinet Office to discuss this very issue. What are we going to do if we have a big storm that produces dose rates that high? Just looking back at January 2012, we'll get reports from Delta, we'll get reports from all the major airlines telling us every time they get impacts during these big space weather storms. This one was interesting for a couple of reasons. One, the very fact that it can happen, but every time a satellite launches, they have to get a weather report, right? They also have to get a space weather report. During a radiation storm, depending on the threshold, depending on the vulnerability of the spacecraft, they'll delay the launch. Energetic particle can penetrate, causing a problem with the navigational system. You could lose the whole mission. So there's various thresholds. So we'll work closely with the United Launch Alliance, SpaceX, and other companies, making sure they have the information necessary. This was the first launch back in out of the Kodiak launch facility in Alaska, 2001, delayed for a week. But I like to show it. Why? Because it happened again just earlier this year. Even with our smaller cycle here, we're still getting impacts. The solar flare delays the U.S. rocket launch. And this was the SpaceX launch to resupply the International Space Station. And they delayed 24 hours due to one of these proton events. NASA spaceflight, I kind of touched on already. We'll be in touch with them. We're in touch with them every day at the Space Radiation Analysis Group, but it ramps up considerably during big storms. They have to make some important decisions of mission control during various phases of the orbit of the International Space Station. And I always like to throw that out there that, yeah, even in deep space we've got issues during these big radiation storms and whatnot can affect our missions in deep space. So these folks want to know what the radiation environment might be like in Mars or Saturn, anywhere where we have our NASA missions. The last thing I want to touch on was the geomagnetic storms. Mostly the big piece. We look at it, we see the sunspots, we see the flare, we see the energetic particles increasing. We turn our attentions to the coronagraph and we see something like that. Terrific explosion of material, magnetic cloud. I'm more concerned with something like this, the halo coronal mass ejection. Now I know it's coming towards us. And we have 5 things we have to do in the Space Weather Center. We have to determine whether the CME occurred. Is it Earth directed? How fast is it moving? How hard is it going to hit us? And how long is it going to last? They're the responsibilities on our forecasters to answer those questions. Fortunately, we do have the Enlil Model. I think you've seen that running already. It's very important in our operations. It's turned out to be quite useful. It's generally plus or minus 7 hours or so, which is not too bad. Certainly with something that's taken 80 hours to get from the sun to the Earth. But we will issue a watch. So this is the key thing. In a forecasting capability, we can issue a watch. So much like a hurricane sitting offshore of Miami by a couple of days, the Hurricane Center issues a watch, giving the whole shoreline a heads up. We've got something coming. We can't pinpoint where it's going to make landfall. We know it's coming. So we do the same thing. We'll issue a watch, giving 12, 24, 36, as much as 72 hours notice, especially to the power grid, that this thing is Earth-directed. And of course, it'll make that 92 million of the 93 million mile transit, hits the A spacecraft, then we'll issue the warning. Now we know. Now we've got that I mentioned that one of the holy grails earlier. Any kind of pre-eruptive signature for a flare. One of the other holy grails is, of course, what does that CME look like when it left the sun? Because we really don't know enough about it till it gets to the A spacecraft, and especially the magnetic cloud, the magnetic field orientation. That's going to influence how the CME is going to impact the geomagnetic field. But as soon as it hits that spacecraft, we issue the warning. The power grid, hopefully we're expecting it because they got to watch. They'll take necessary action and hopefully protect the grid. So what are the consequences of these geomagnetic storms? Just a couple of examples. We'll go back to our GPS customers. This is the Wide Area Augmentation System, introduced back about 2003, that the FAA, the Federal Aviation Administration, uses. On the color scale on the right, it's the vertical error limits. Blue is good. Once we get up to the yellows, especially into the reds, this system is essentially rendered useless when we're into the reds. In October 2003, those Halloween storms, we could take a look at what happened. Geomagnetic storm begins right about now. We'll see the degradation working its way from the south, moving its way north through Texas. Most of the northeast is gone, in the northwest. And for 11 and 15-hour periods, the system was rendered useless, essentially. The ionosphere was so disturbed, and the signal was so degraded that we could not use that GPS-based system. So it's just a good example of remember the first one we talked about the burst at 1.6 gigahertz, lasting short periods of time. This, obviously, is not a short-lived storm. It just makes GPS more accurate for them, essentially. So when they're flying a plane and they're using the GPS, it's a correction system to make sure it's perfectly accurate. And in situations like this, it way exceeded its error bars. It was the integrity was never compromised because the system is built so that pilots are told not to use it. So they're not they're not relying on the triple redundancy built in, and they're not using it, they're not getting bad information from it. So they always stress the integrity is never breached. The power grid issue is the biggie. We get the CME, the geomagnetic storm begins. We'll see currents flowing in the magnetosphere, the ionosphere. They manifest themselves on the ground in the way of geomagnetically induced currents, can flow right into our power grid. When they do, they can cause all sorts of problems. In a worst case scenario, they can damage transformers and cause a blackout. One of the consequences from the US perspective, it's significant, and it's this. When we look across the world on the vulnerability to this phenomena, we've come to the conclusion that the most vulnerable place in the world is the corridor between Washington, D.C. and New York City. Not good. And it's largely due to its latitude, location relative to a large body of conductive material, salt water. Conductivity of the rock, geology is critical, plays into it very much so in the Northeast. And of course you have to have that big interconnected grid. It's all there in the Northeast in particular, and it's caused considerable concern. Why? Because some engineering reports came out and suggested, as was the case here, that inside that dark black line, on an extreme Carrington-like event, we could have transformer damage, up to 300 transformers. The consequence of the outage, the blackout, not being in hours or days or weeks, but months and even years. It would be civilization changing if something like that occurred. So again, that got everyone's attention. If this is indeed credible, if this is indeed a vulnerability, we need to be doing something about it. And that question, is a 50-year storm, a 100-year storm? Would a Carrington-like event do something like that? A lot of unanswered questions. Carl's on the back. He's done some good work published recently looking at some of this stuff. There's a lot of unanswered questions. I always like to explain to our leadership that this is not theory, this has happened, just not to any great scale. But we had the March '89 magnetic storm that brought the grid down in Montreal and Quebec. 1991, some of our big nuclear power plants in New Jersey and Pennsylvania had transformer damage due to one of these geomagnetic storms. And as recently as the Halloween storms in 2003 brought the grid down in Malmö, Sweden. So it does happen. The vulnerability is there. We know that. But what if it's a Carrington-like event? What would the consequence be? That's what everyone would like to know. That's what a picture of the transformer damage looks like. Actual physical damage to the windings, the leads into the transformers can actually burn up. They have lots of procedures in place to manage this, but do they have procedures in place to manage the extreme event is one of the big concerns. But that's a standard operating procedure from the New England Independent System Operator showing the different things they will do during a big extreme geomagnetic storm. And that other plot there is just the U.S. Nuclear Regulatory Commission power reactor status. And I like to show that to people even as far south as Palo Verde's, the biggest nuclear power plants. They're down in Arizona. They'll all take action across the nation during these big geomagnetic storms. So we'll just finish up with just a couple of comments on the government response. I've kind of laid it out here, the societal impacts. You should have some sense why there's a lot of people concerned about this and what are we doing about it. One of the key things was the group responsible for the oversight and security of the electric power grid in North America, in the United States, I should say, is FERC, the Federal Energy Regulatory Commission. In May of last year, they issued an order that all power grid entities in this country would introduce some kind of response procedures to a geomagnetic storm threat. And they would also do vulnerability assessments so they could understand how vulnerable their systems are. That's an ongoing activity right now. The North American Electric Reliability Corporation have put together a task force that have brought industry together from around the country and indeed Canada to figure out how to best handle this threat. The White House has a geomagnetically induced currents interagency working group. I'll be there at the White House on Tuesday with this group to brief the National Security Council and the Office of Science and Technology Policy on our latest developments. There's been major exercises and across the world international activities under the UN umbrella and bilateral activities with the United Kingdom, South Korea, Sweden, and many others, all in the last couple of years in response to this threat. It is now included in our national risk register, right there under hurricanes and above tsunamis, giving it that kind of respect. And once it's on the risk register, then things have to be done in response to it. I'll finish up with this. Somebody had mentioned it earlier about the communications, using the can with the long string. One of the FEMA guys, during a visit to the Space Weather Prediction Center, was worried he'd have no communications during a big space weather event. You know, HF, SATCOMs would be affected, and he made the comment to me, well, Bill, I guess we'll just have to go back to using messenger pigeons. And I had to say, no, they get impacted too. And he couldn't believe it, but they do. And it's the people, we've, in the forecast center, we'll get calls from the power grid, from NASA, from the DOD, satellite operators, but the one I fear the most is the pigeon racer. Because those folks who, anyone here involved in pigeon racing before I go any further? Okay. Well, it's a big thing. It's a world sport, but they head up to leave Colorado and head up to Nebraska and have a keg of beer and a barbecue and release the pigeons, and the first one home wins. They rely on the magnetic field, the Earth's magnetic field, to navigate. Even during a moderate level geomagnetic storm, they can get lost. And in the bad storms, they don't come back. And you know, I looked into this because I had read a little bit about it. There was a big pigeon race, and the prize was like $500 or something. I said, well, you know, okay, so if you lose the pigeon, yeah, but it turns out it's a big gambling sport as well, so there'll be a lot of money put on these birds. They call it a pigeon bust. The pigeons get lost. So it's an actual real consequence and concern. And I had one other funny story about the pigeons. So I had a company signed up for the alerts and warnings a couple of months ago, and it was called Serenity Doves. I had to call and ask them why they were getting the information. She said to me that we're one of the companies that released the doves for weddings and funerals. And they had read something in one of their magazines that pigeons, their doves, could get affected by geomagnetic storms. And yeah, we talked a little bit about it, but you know, if you're at a wedding and you see the doves released and they fly over, they flutter around in circles almost in honor of the bride. Of course, they're getting their magnetic field, their magnetic bearing. And once they get it, they're gone. Heck with the bride. But I did ask the woman, I said, let me get this straight. So you're standing outside the steps of the chapel. The bride and groom walk out. The pigeons are ready to go. Your cell phone rings, and it's Bill Murtagh with a geomagnetic storm warning. I says, and you're not going to let the doves go? And she says, yeah, I guess. I says, good, because I want to be there when you tell the bride that you're not letting her doves go because of a geomagnetic storm, just to see that face. Anyway, I'll leave it at that, and I don't know if we have time for any questions or what, but thanks very much for your attention.
I have a quick question, Bill. So you could respond to this and say the answer is we need more data, we need more science, we need to know about the sun and magnetic response. Give us more money to do space science. That could be one response. The other response could be to heck with space science, you're never going to be able to predict it. Let's engineer our way out of the problem. So where do you stand on that?
Well, right in the middle. and for good reason, because I think the FERC ruling is perhaps the best example. They took their position right in the middle as well. There is no question in their mind about the value of a forecast, because even the engineering plan, some of the engineering solutions still require some level of response to the geomagnetic storm forecast. So they really appreciate the level of the value of the forecast, but they also recognize that we don't get it right all the time. So to be relying on a forecast for something that could be so devastating is not a good idea. So let's engineer around the problem as much as possible. So the discussions are twofold. They are how can we improve the forecasting process? How can we engineer around the problem by introducing blocking devices, capacitor banks, and try to understand if they'll actually do what they're supposed to do. But generally, for the most part, and it's across the board, there's certain things like the scintillation and its effect on the GPS that you'll never really engineer around. So there'll always be a place there for the science and the forecasting, and I think that's what we're seeing. So it's encouraging from us in our business, in the science and operational world, the value put on the forecast continuously. Well, I recognize if we can engineer around some of this stuff, let's do it. And just one other example on that, Fran. The guys that are flying the polar routes are using, some of them now have put iridium. The geosynchronous satellites that we use typically for communications are, of course, are over the equator. So once you get past about 82 degrees north, you can no longer talk to the satellite. You lose the capability. But with a LEO fleet, the iridium, they can communicate. So some of them have introduced the iridium. But it was explained to me that costs money, so they're still relying on HF. But now they want the forecast, and they want to be ready with a backup for safety flight issues and whatnot. So it's a good balance, I think. Yeah.
What additional data would most improve?
You should go to the White House, because that's the question. That's why we're going to be there Tuesday. They want to know what additional data. So there's a couple of things we're focusing on. That's the kind of question you could spend the rest of the day talking about, because various reasons. But certainly, if we had a spacecraft, I'll start with there's a mission called Sunjammer, which is use of the solar sail technology. If we could have measurements further upstream than L1. My background was meteorology. I know when a cold front comes through Memphis and it's cutting its way across, I can time when it's going to hit Washington, D.C. I'd love to be able to do that if I had some spacecraft upstream from the L1. So yeah, that would be fantastic. If I told the power grid guys, instead of 30 minutes heads up, I'll give you 2 hours, they'd love me to death. They think that would be great. So yeah, so if we can get that kind of data. And what if I had a spacecraft sitting, you know, the L5 point? Okay, if I have a spacecraft over there taking pictures of the sun, Earth for the CMEs to really get a good sense of how fast they're moving and how they're evolving, that would be tremendous. Stereo proved that to us when it was at that location for a few years, how nice that would be. So we've actually included L5 measurements now in our requirements document. Radio occultation information. We're talking about doing with the Cosmic 2. We get it from Cosmic 1, but there's tremendous efforts underway, even discussions this morning about getting that information into the Operations Center in near real time so we can really specify and hopefully predict ionospheric changes, because it's very difficult right now over the oceans. Guess where all the drilling's going on? Over the oceans. So if we can get 10,000 soundings a day from the occultation and really capture what's going on, the dynamics of the ionosphere. So there's so much. One of the exciting things about this business is there is so much in the way of opportunity, both in the observational arena and in the research and modeling, because there's a lot of questions that are unanswered.
Well, you showed that your number of customers has
Yeah.
in the past year. Means that it's going to continue to
Mhm.
increase. So in your opinion, how is this field going to look like?
Yeah, I think it gets back to that initial question about if we engineered around all the threats, maybe we'd be much more interested in the science of space weather than the operational side of the house. Well, I do not believe that's going to be the case. I think that each step of the way, as our technology evolves, we introduce new vulnerabilities. And I think that will continue. It happens, when I see the microchip technology and how it's advanced over the years, and it's fantastic, but it is vulnerable to space weather. And I don't see us ever getting to a point where we'll ever engineer completely around these issues. So I think there'll always be an important place for the science and operations of space weather. Yeah, Tony? Yeah, we weren't able to quantify it. The question has come up to us because we never really look. There's so many variables that come into play when we relied on the chronograph alone, the SOHO-LASCO alone in the last cycle. And the stereo, the big problem with trying to quantify the value of stereo is quantify it for which periods, because it's of varying quality, the data. When it's sitting near the L5 point and it's a 90-degree angle off the Sun-Earth line, we know it was much better than where it is right now in helping us understand what the CME looks like. So we haven't been able to quantify it, but just working with NASA last week, in fact, trying to understand what the consequence is. It's there. There was a degradation in the quality of the product, but how much, I can't just say yet. Carol.
I have a comment and a question. Everybody here. In this school, we're not going to get into the details of these technologies.
Yes, absolutely.
Hi.
The question is this: when you commented on the question, I understood that what we really don't know is the magnitude of the geometry. Or how the geometry actually respond to that right.
Yeah, one of the things we're doing is, I didn't cover it in the talk today, but we're introducing this Sun to Earth modeling framework. So we bring in WSA, Enlil, and we're just in the process of transitioning now to geospace model and the whole atmosphere model. And that last piece is what's happening right here on Earth. So we're trying to model the E field. And the key piece here is the power grid wants something specific to their location. Because when we talk about the K value, or that G scale, we're talking about a global forecast. I'm saying that a K6 is going to occur. That's strong levels of storming in the Earth's magnetic field. Now, what good is that to a guy operating a power plant in Maine versus the guy who's operating the Palo Alto plant in Arizona? So we want to get down to where we can do regional specification. So certainly one of the things we'd like to do, and we're trying to understand how to best do this, is in order to get a good, accurate E-field model, to understand regionally and locally what the electric field might look like, and of course, consequently, the geomagnetic induced current, what kind of a network of magnetometers or even E-field measurement do we need? So go back to Tuesday's meeting, USGS will be there because we're exploring that right now. So those critical observations right down here on Earth's surface play in. Is that where you're kind of going with yeah. Yeah.
And indeed, what Helix is going to be talking about ionosphere, the astromagnetospheric coupling. Saturday, I'll talk a little bit about the magnetospheric response to solar wind. So we will be talking more about the science of this. Very, intellectual level, but indeed, understand the system better as a system. What those response to the solar wind.
Right. Yeah. Yeah, there's no question. And one of the, as you go through your class here, you'll be talking a little bit about the BZ and the coupling of the southward BZ. Recognize this, that when we look closely at the Halloween storms, and I can provide the plots if anyone wants to see it, we looked at exactly what the magnetic field, the Z component, looked like against the actual induced current on some of the grid components. And the strongest geomagnetically induced current occurred during the very strong northward BZ, which is just a reflection of just how complex that process is, but you'll learn why that happens. I'm still trying to figure it out.
Thank you. Thank you for
Very
that.
fun.
Feeds in well. Excellent.